Hi, everyone. Good afternoon. I hope everyone here knows my name. I've been your TA for the past 10 weeks or so. It's great to see everyone's faces. While I have my moment in the spotlight, I want to take a minute to say thank you for being wonderful students. I will be hosting office hours on Friday and on Tuesday, and we're looking forward, the graders and I, to review your final projects. We're excited to see where you take it from there. Okay, so with that little 5-second spiel said, let's get started on this lecture titled close-range vision-based pose and shape estimation. So we'll start with a quick introduction to the topic. Why should you care about this whole discussion? What are the challenges that we face? And then we'll cover some key examples, one in classical computer vision, and then a couple in machine learning. Then I'll give you a demonstration using ML. Demonstration is a big word to be used for what I'm going to give you, but we'll provide you some code that you can then use in your final report as part of your bonus. So I think it's a kind of a neat thing that you get to do. And then we'll conclude with some final thoughts and kind of next steps in this world of research. So we've spent kind of a big part of this whole class talking about dynamics modeling, control, navigation, and what we've noticed a lot is about passive safety. And what we care about that is because we want to avoid collisions. And as we get closer, those collisions become more probable. And so the title of this presentation, if you remember, was close-range vision-based pose estimation. And so the question might be, why get close, right? Collisions can have really catastrophic effects, such as like the loss of the asset, in this case, the satellite, or whatever target you might have. And so that can lead to mission failure. If enough of these happen, you can get something called the Kepler effect. And then if we're talking about human spaceflight, obviously we can be dealing with loss of life. So when we talk about getting close in space, we have to be really careful that it's well motivated. And so the fact of the matter is, though, that some of these missions that we're going to talk about are either simply not possible or they're infeasible, either economically or just from a technology perspective, to be carried out by a single spacecraft doing its own thing. And so it's much more effective to use multiple spacecraft. And so that calls for the increased complexity and risks that are associated with kind of getting close, and even rendezvous and then even docking. And what are some of those examples? Well, I think one of the most obvious ones is the Apollo missions. We started this whole class talking about the 3 problems that DSS systems can help you resolve. And one of those was kind of the rocket equation. And so not having enough fuel to get your payload out there, and how do you deal with that? And so the Apollo mission did this by doing a rendezvous in the moon. So that's one example of why getting close in space might be worth it for you. Another example is to avoid replacing an existing satellite that's working, but just so happens to be out of fuel. So I know some of you are working on the MEV mission for your projects. And so this is an example of the MEV mission carrying out its refueling of the Intelsat satellite in February of 2020, so about 5 years ago. And I think it actually just undocked pretty recently. We can also think about not just refueling by fixing an existing satellite. That might be a reason to go up there and get close and even dock. So this is an example of the shuttle kind of deploying Hubble back out there after after one of the missions that were sent to fix it, either the lenses or the gyroscopes. Additionally, we can think of getting close to kind of dispose of a broken satellite. So this is an example of the ClearSpace mission. But satellite is a bit of a specific term, so we can also think of anything else that's out there in space, such as rocket bodies. So this is an example from the ATOS-J mission from Astroscale. And so you're seeing some of the images that were taken during that mission of that upper stage of the rocket body. And I'm sure you can think of a lot others, but this is just kind of to give you some sort of motivation as to why we've spent a lot of this class talking about proximity operations being dangerous. This hopefully helps you motivate why we might want to do them in some cases. So now we know the why. Let's figure out what we need to do in order to achieve this safely. And for the most part, for all of these missions, what you require are position estimates with respect to your target. So that's how you avoid collisions. And a really clear question and really common question is, why don't we just do differential GNSS? I think we've had 2 or 3 lectures on this topic, so I think that's an obvious thing to ask. And there's 3 potential reasons, and I'm sure there's many more, but this is just some examples. One of them is that in deep space, for example, GNSS is not always available, and so you can't rely on it then. And then the other 2 are kind of sort of related. And that's in the sense that your target might not be able to help you do differential GNSS, which is required. And so one reason it might just be that the target's not equipped, so it has no inter-site link for it to share those GNSS solutions, or it's defunct. It's not even trying to solve its own absolute orbit, and so there's no way it could give you its kind of GPS measurements. So in these cases, we turn to what are called uncooperative methods, in which case we purely from the servicer estimate the target's kind of pose. And I have an image here to help you talk about these things. So generally, when I say the target, it's the thing that we're trying to image if we're talking about vision-based pose estimation, and then the servicer is the thing with the imaging device, like a camera. So in uncooperative methods, what we're going to try to do, and this is kind of more of a general problem statement, is to use some sort of servicer, a sensor on a servicer to determine the position of an uncooperative target relative to the service's frame. And then we're going to do this either using a single or a set of measurements. If we're docking, we're also going to care about the attitude of the target. And then in that case, we're going to talk about the pose. And the pose is just a combination of the position and the attitude put together. This lecture, though, was titled Close-Range Vision-Based Pose Estimation, Pose and Shape Estimation. So let's talk about the shape portion of this. And that's if the target is unknown. And again, a really clear question is, why would the target be unknown? And there's kind of three main reasons why. The first one is that companies and countries don't readily release CAD models of their space assets. So in general, you can't really assume that you're going to have those. And then the other two are, again, kind of coupled. The satellite doesn't look as it does in our CAD model, either because there's been a deployable failure, so say the solar panel was only half deployed, but you don't actually know that 100%, and so you don't actually know what it's going to look like, or it's been in a collision, and so now really we have no idea what it might look like then. But for safety reasons, we're still going to want to estimate its position with respect to us, and since the position and the shape estimates tend to be coupled, you generally want to estimate both at the same time. So now let's, again, dig further into the actual title of the presentation, which was about vision-based pose and shape estimation. And so the general problem statement becomes a bit more specific, where we're now going to use a monocular camera as our sensor to do pose estimation of a servicer using either a single or multiple images. And if the target's unknown, we're also going to want to do shape estimation using those same images. And why use a monocular camera? The reason for these is kind of threefold. The first one is that they're kind of low SWaP-C, so that means they're inexpensive to put on a spacecraft, and it makes the spacecraft more inexpensive to launch. It also allows for sensor redundancy, so you can think of like stereo vision methods might be more robust, but then if you have a sensor failure on one of your cameras, you're down to one camera, is your mission gonna not work anymore? That might be the case, but if we're focused on monocular cameras, we might be able to overcome this limitation. And then finally, in general, cameras have a pretty high dynamic range. So last week, 2 weeks ago, at some point, Justin gave a lecture on far-range navigation. Right, those cameras were being used in navigation at about 100 kilometers of range, and now we're talking about using them for about 10 meters. And so you can get a sense of that dynamic range there. Sounds like everything's great, but not really. As Justin mentioned, when we go to the camera world, we get a loss of information. We go from a 3D to a 2D projection that inherently loses information. And so that's a challenge to be overcome by these algorithms. In space, we also have a really harsh imaging environment. And so that means that we get sparse, meaning infrequent, and noisy images. And so you're seeing some examples there where the lighting is not so great for imaging. And then finally, we're dealt a pretty bad hand in space, and we have pretty bad computational resources when we're talking about spacecraft. So we have a couple problems to solve, right? Pose and shape estimation. We have some challenges. So now we're going to look at some examples of how people have overcome this in the past. We'll start with a classical computer vision approach. And the approach taken here is to do kind of an initial estimate of the pose and then to refine it through multiple steps. So I'll get more specific here. The way that the pose is finally determined is by doing what's called feature detection. So in particular, the features here are lines. So they're using what's called canny edge detection, which is a kind of typical computer vision approach to detect lines on this image. So these are the lines it's detecting. Then it does what's called a hue transform. If you've heard of ransack, it's kind of a similar process, but a bit different. To detect what are straight lines. And why we might care about straight lines is because those are easier to interpret later down the line. And then finally, you see the output kind of overlaid over the RGB image that was, sorry, grayscale image that was originally taken, is that you're going to have some edges that you fully kind of detect and some edges that you don't fully detect. So those are partial edges. And so the goal then is to estimate a pose, as in a position and orientation of the target, that would lead to those edge detections. So that's kind of the problem statement that this tries to solve. So the first step in doing that is by sampling poses. So what do I mean by that is, okay, I know what my target actually looks like. And so what I can do is I can project it to 2D space if I know a pose. And then I can try to match the projection to these lines that I've now detected on the image. And so then I can get some feature error, right? So if I know that this line is like over here, and then on the image it appears over here, I might have like 100 pixels of error, say. And we might say that that's then a bad pose estimate. That's kind of the notion. So you can also get smart and sample poses that are feasible. So you're not going to sample a pose that's behind you, because the camera can't image that. And in general, the camera has a field of view that kind of looks like a cone. So you can sample poses along that cone. So then you reduce your search space quite significantly. And instead of searching all over the world, you search specifically along that cone. So from there, you project it 2D. You try to find the lines on the projection with respect to the image. And then you can calculate an error. And then what they do is they select the set of poses which have less than 100 pixels of error. And this is 2 examples of them. So you're seeing that they're okay, but not great. But we're not done. The first step in the refinement process is to do an initial refinement by walking the pose guess, if you will, through a cone. And so that leads to these 2 estimates. So we started with these, and then these same initial pose guesses get refined by looking at, again, that same error that we were talking about before, right? You get a pose, you project it 2D, you compare with the lines that you saw in the image, and that gets you an error. The error is minimized by walking around the cone. So again, these are better, still not great, but we're not done. There's a second refinement step now using Newton-Raphson, and this gets a lot better. This gets about 2.5 pixels of error. Great. But we still have 2 kind of potential poses, if you will, pose candidates, that have roughly the same amount of error. And as humans, we know which one's correct, right? This one is much more correct than this one, which has kind of a flip about its axis. But from a computational perspective, there's no way to know that currently. And so we'll solve that in a second. But I want you to keep that in mind as we talk about the next step. What we're going to do next is we have these pose estimates. We know roughly where the lines should be. So we're going to try to find more line matches in the image, right? So we started with, these red lines. We're going to try to find more of them by using our pose estimate. And the one pose candidate for which the projections get more new line estimates is our winner. And then we throw our hands up and say, hooray. This is this one, right? You see that it's got this new one, line segment, and this one doesn't get that match because the pose estimate is poorer. And so that's the way that choice is made. I can tell by your faces you're all confused, and that's one of the limitations of this method. It is more complicated. It leads to more confusion. But when you deal with it, it's not too bad. So, okay, Prash, do you have a question?
So you said this was sort of like a ransack method for detecting edges.
Yeah.
And typically for that, you sort of supply it with a data set and it tries to fit a line to that data set. So I'm wondering how you automate the process where you give it individual line segments for it to do the thresholding. Sort of just unclear on that.
Yeah, so I would say the example you're providing is an example of an application of ransack, right? Ransack is random sample consensus, something like that. You don't have to fit a line in ransack. You can fit whatever function you want. In this case, the data set is these lines that we've imaged. So it might be the points, for example. and then you try to fit straight lines onto those points using the Hue transform. It's a bit different. You like map to a different space that becomes a bit easier to then find minima. So in Ransack you do like random sampling. Hue transform doesn't do random sampling, I believe. But then computationally it's more expensive, ends up being. Gives you a sense of.
Can I give a little bit of context?
Absolutely.
Because Paul took the initiative to pick this example. This is the first publication ever I made on this topic. So we're talking about 2014, probably, so, something like that. I was on a sabbatical at Danish Technical University from DLR, and I had access to the Prisma flight images, and I developed this approach during the sabbatical. Obviously leveraging some of the previous experience on the topic. So it's interesting that Paul is starting here because this is the beginning. So from the table of content, he will get to the end, which is the most advanced methodology that we use today. Something I wanted to mention here is, okay, there is an upgraded version of this method in Sharma, which is covered in some of my slides. But one key feature of this approach is, in order to reduce the search space in terms of features, because we need to match features in the 3D model with features on the image, and they can be, a lot of ambiguity of what feature correspond to. We group them. At the time, I call it perceptual groups, and we group them in parallel lines or trapezoidal or other shapes, so that we reduce the number of pairing we need to do with the 3D model, because there is a reduced amount of this group of features in the available 3D model. So that's one of the approaches to speed up this technique. I finish here with a comment to, I like that you started from here, and I'm curious to see where it gets.
Yeah, no, absolutely. Thank you for pointing that out. I should have said that this was the first to do this, and that was the goal, to show kind of the progression as time has gone on of people trying the same problem. We're closer to a solution, to be clear. It's a bit of a spoiler, but we're still working on it. So don't think that this is a solved problem. It's still an active area of research. Cool. All right, kind of spoils this slide a little bit. You might think that from this pose estimate was going to be my pitch. We're done, right? We can probably wrap up this presentation, at least on the pose side, and call it a day. Go home early. Not quite.
Well, in practice, they do.
In practice, yeah. In practice, yeah. But
don't like the machine learning.
No. Yeah. Yeah, a lot of people don't. Yeah. But we're going to keep going because there's a couple limitations. First, the actual algorithm that I'm presenting on here is a complicated system. You can see all the different blocks that we talked about. So this was kind of the initial post sampling. This was the cone refinement plus the Newton-Raphson step. And then this was the model matching where we're trying to find new lines or trapezoids. Convoluted has some hyperparameter tuning to be done, and that can lead to issues at the end of implementation. Additionally, it has a bit of a general lack of robustness to elimination conditions due to the canny edge detection, which is just not super robust to that, and to background conditions. And so this is some Prisma images in flight, and you can see that the elimination conditions really change, and that sometimes we have the Earth in the background. It doesn't really collaborate with us that well. And so that can lead to difficulties for these kinds of methods. And so due to these limitations in this kind of classical approach, we turn to, again, spoiler from before, data-driven methods to try to resolve these. And so, especially with the advent of machine learning after the release of, I think, AlexNet in 2012, computer vision has really exploded in the field of ML. And so a lot of the new literature focuses on kind of training neural networks for this task. And then a nice little, from a presenter's perspective, point of view is that we can reduce this kind of more complicated model with a lot of fine-tuning to a pretty simple model with a neural network. This is an oversimplification, but we'll get there. So the next problem, the next kind of attempt at solving this problem that I've chosen to present on today uses two convolutional neural networks and borrows architectures from MobileNet and YOLO, which are kind of famous CNNs for their potential and use cases. And this was a paper released in 2019, and so you might be asking yourself, why am I presenting this in 2025? Well, this paper just happens to have, or a very similar version of this paper has a MATLAB implementation that then you could use in your final reports as kind of a nice bonus. And I'll present on that at the end, but just as a kind of reasoning for picking this paper. So to show you kind of the full architecture of the paper, step one actually has nothing to do with the CNN. It actually has to do with generating a data set to train a neural network. I'll get more into that in a second, but at the end of the day, what we need to do is to collect images to then train a neural network to do our pose estimation for us. So how do we actually do pose estimation? Well, when you take an image of a satellite, as you can see from this example over here, a lot of it is like black. And so it can be more difficult to do pose estimation on just black. And it's better to do it on a picture that's just of your target. So the first thing to be done is to do, they train an object detection network. And so this creates kind of a bounding box around our target. And then we feed that into a key point regression network. And so what you feed in is kind of this crop version of this bigger image that has been determined by the object detection network. Then we pass that through a couple CNNs. And then what we get are estimated key points on the satellite. So before, on the first method that I presented on, we were detecting lines. Now we've switched to just key points, and that seems to be sufficient to get the pose, because we can do what's called the perspective endpoint problem, which solves for the 3D position of a target given key points in an image and their respective 3D locations with respect to the target. So that gives you a sense of the kind of problem we're solving. It's a very typical problem in computer vision, easily solved. And so that's why they chose kind of this approach. So this seems super nice and relatively simple. But kind of thing that I haven't really talked about too much right now is how to train this neural network. And so something about space that makes it more difficult is that it's kind of far away. And so to get space images, we need to go to space. And so maybe you want to train some neural network to then go to space and do some task, like dock with another spacecraft. So to do that, you might need to go to space, take images of the spacecraft. Somehow, you're being safe about that. We don't know how. And then you're going to return those images back to the Earth. You're going to train them on those images. And now you can launch again. And so all of this seems rather convoluted. So a lot of people turn to synthetic images. And so what you do is you get some sort of rendering of your target, and you put it on different kind of relative positions, and then you train your neural network on that. Sounds great. Not really. There's kind of a problem when we train neural networks on synthetic images, and this is called the domain gap. And so that's the difference between synthetically generated images and true images. So here you're seeing images rendered in the Unreal Engine versus the real Prisma images. And so a couple of things immediately that you can tell that are different is the lighting, right? And then if you pay really close attention to Tango, which is the spacecraft over here, the textures also look different. And so it's kind of difficult to model these things in synthetic rendering. Certainly, given enough time, it will be feasible, but it's not currently done. And so we have to deal with this domain gap. Kind of a way to overcome this is to train the neural network on a larger distribution of data. And the way to do this is that you kind of mess with the lighting in your rendering, you mess with the 3D model, and then you mess with the textures a little bit to get the neural network to train on a larger distribution of data, and then hopefully it works on the real data. Something we've been doing at Slab quite a bit is instead of just doing those two steps and then launch into space and hope that it works on the real space images, we've developed a kind of a space surrogate environment. So the thought process is you train on synthetic images, and then you go and test your neural network within the space surrogate, And then that gives you a sense of your domain gap, as in what is the gap between my synthetically trained neural network and my space surrogate, and that can give you some sort of sense of what your gap would be between your synthetic and your real space images. So now we've talked about how to train the neural network. We've talked about the architecture. Let's talk about performance. This is kind of giving you, let's start at your right-hand side. So over here, you're getting the error in the translation estimate. So again, the full process, right, is we take a picture, we get a bounding box around the target, we then feed that to a key point regression network, we get key points that are detected, and then we solve the prospective endpoint problem to get the pose. Okay, so now, this is the pose error. In particular, this is the position error absolutely talking about. And you can tell that on the x-axis, this is the relative distance between the target and the camera. As we get closer, the translation error gets better. Kind of makes sense. And then likewise for the rotation error. And then over here on your left-hand side, you're seeing kind of 3 rows of 3 different examples of the network doing a good job. So the first one is one where the target is quite close, almost like it's not fully in the frame. And so you see that the network is doing a good job in bounding around the target, and secondly, in getting the pose estimate. The way that we know that the pose estimate is well estimated, that was a bit of a roundabout way of saying that, but is that we take the pose estimate and then we project the 3D wireframe onto the image, and then you can kind of visually pair that. The second one is one where maybe we're like near eclipse, and so the lighting conditions aren't so good, and still the network is doing a good job in estimating both the relative location through the object detection network and the precise pose with the key point regression network. And then finally, when it's further away and even when there's background in the image, so now we've overcome that previous paper that I was talking about, we're still doing a good job in detecting the satellite and getting its pose. Okay, great. So now really, I must be done. But no. Oh yeah, of course.
Intuitively speaking, why does the rotation error increase so much when you're pretty close?
Yeah. I can think of a couple reasons. One would be that you're so close that not the whole satellite is visible. And so it has a harder time kind of estimating the location of features that are not in the image, which is fair enough. Another reason could just be lack of training data in that regime. So you might be in a more data constrained regime just due to the choice in the synthetic data generation. And so that might lead to worse error in the orientation.
With the neural network, why is estimating the lighting something to worry about?
Estimating the lighting. Yeah. What do you mean by that? Sorry.
You were saying that like the output from the neural network a couple slides ago it showed like a different lighting from the real thing. Why is that something to worry about? Like from this slide.
This slide, right?
Yeah.
Okay. Yeah. So the general thought process with what's called the domain gap is that when you train a neural network, you are training on some data set. And you can think of this data set as a distribution of images, right? It's a distribution of data at the end of the day. And the neural network is trained to perform well on this particular distribution, and you have no guarantees that it'll work on any other distribution. Now, the real space images are a different distribution. They're similar, but they're different. And so you have no guarantees that your neural network will work well on any other distribution, including space images. Now, again, there's like fuzziness there because they are quite similar distributions, but they are actually different. And so that's why we kind of introduce data augmentation techniques to kind of expand that training distribution, and then hopefully within that new wider distribution, there exists the space images.
To give you a very practical example, your computer graphics renderer might not be able to model properly how light interact with the material and surface of the target satellite. You could have a reflection from the sun, a glint, an overexposure, and then all of a sudden part of the image gets very bright. The net is not able, if it has not been trained on that kind of situation, to detect the key point. where is now the edge of the satellite, because it's it's not visible. Similar to the problem your eye will have in guessing where is that feature. So just to give a practical example, so they can be wild, the variation of illumination condition.
Use Tron to test, not to train the neural network?
Correct, yeah. So the thought process is that we want to understand what your performance is going to look like once you actually launch to space. If we train on Tron, as in if we train on images that are coming from the space surrogate environment, it's almost like saying we had real space images available for training, which limits the actual whole argument.
Yep.
That we will be able to overcome the domain gap once we go to space.
The kind of cheating, from our perspective.
But you use Tron to generate some data sets to train other ones on, or not?
In general, we generate those data sets to validate the neural network.
Okay.
You can think of it like if you've done machine learning before, like your training, your validation, and your testing set, you can think of Tron as like the test set.
Yeah.
When you're generating the data sets, you're basically basing it off of like existing node satellite shapes.
Yeah, so in this case, a lot of the data sets that I've been talking about are going to be of a single satellite, right? Because we're only interested in estimating the pose of that one satellite. Bit of a spoiler, that's the next topic, is doing multiple satellites. But yes, currently the approach has been to take known existing satellite 3D models and use those in rendering.
What about for like pose satellites, dimensions that we don't know anything about? Like say, for example, you want to try to image like completely unknown space triangle, completely unknown like foreign satellite. Like what's the process to then like predicting what's going to look like?
Give me 5 slides. Not even?
Okay.
We'll get there, I promise. Okay, fantastic. So, again, here's my pitch again of we must be done, no we're not. Again, this paper was released in 2019, and so there has been a lot of work done recently. I wanted to cover this work first because I think it's pretty easy to understand from a first glance perspective, and second of all because there is that MATLAB implementation that you can use in your project. But just to give kind of a quick overview of what some of these works have been doing, there's still improvement to be done, right, in the pose accuracy and the effects of the domain gap. So we can still do better than the degree level rotation estimates, for example. And then we also want to reduce the computational load and to run it on space-grade hardware. And so that's something that's been done for some work after this. We can also think of robustifying this whole thing with a filter. So here I'm just giving you like raw measurements. Okay, now let's actually implement this into a filter. What does that look like? How do we do like outlier detection when the images are so out of distribution that we never actually modeled them, for example. And then we can also very recently improve the performance in flight with online retraining. So once we actually start receiving real space images, let's do a little bit of fine-tuning of our model so that then it actually starts to learn about the different lighting models that you might see in space. And then the one that I don't have a citation for is the one that we haven't done yet, and that's to fly it. So here I'm showing you some results from SPN v3, which is the Spacecraft Pose Network, the third version, obviously, which are the ones that are kind of related to the first 2 citations. And you're seeing that it's dealing with kind of harsher lighting environments, and it's working across the domain gap. So these are images taken in our space surrogate environment, and then these are real Prisma images. And so it's working across that whole pipeline. Okay, as Sid mentioned, the one thing we haven't talked about is unknown targets. And so that's my next slide, as promised. So yeah, what if the target is unknown, right? All of the methods that I've mentioned, so the 2 methods that I've mentioned so far have dealt with, we know what the target looks like, let's try to match some sort of feature on the image, and then map that back to the known target pose. What if we don't know the target? So the work here is much newer, much more fresh. It's much more fun, but much more complicated. So here what this kind of third paper that I'll present on today, they took a CNN and then trained it to estimate both the shape and the pose from one image. And so I'll give you the full CNN architecture, but basically what it looks like is you take an image, you pass it through an encoder, which is kind of a fancy name for a neural network. And then it's got kind of two separate heads that it splits out. And then the first head, what it does is it estimates the shape as kind of a coarse 3D estimate. And I'll show you some examples at the end. But just to give you a sense, it's supposed to be like pretty rough estimates so that the CNN can kind of do something with that. And then obviously it also gives you the pose. And then here it's showing you a kind of, a couple of different losses that it's used to train. But at the end of the day, the important thing to note, it's a CNN. It gives you a coarse shape estimate and a pose. So as Sid very well mentioned, the kind of data that I was talking about before was of a single satellite. And so now we need to deal with multiple satellites. And so with this kind of paper, a data set was released called SPEAR. And so that includes 64 satellites, so not just the one, of available satellite 3D models from, I think, NASA and ESA. And then it renders 1,000 images and their masks for each model using Unreal Engine 5, so for about 64,000 images. And here you're seeing some of those examples of those satellites. Something to note before we go to the next slide is the way that the data set is split is a bit not non-standard. So there's 64 satellites, 58 of those and their respective images are used for training and validation. And then the remaining 5 or 6, whatever, are used for testing only. That means that the network never sees these satellites during training. And so that's used as a kind of a gauge for generalization towards any other satellite that you might encounter out in space that's not included in the data set. It's going back to kind of to our discussion with Space Surrogate. If we were to use those images, like we were talking about with Tycho, to train the network, we'd be cheating a little bit because then we don't know how we're going to perform in space. Same thought process here. We reserve some satellites to see how we would do with real satellites that we haven't seen yet. So, with that being said, the top row gives you kind of coarse shape estimates of the satellites that were seen during training. And you see that it does an okay job. Again, coarse, but it's pretty good. The bottom row, on the other hand, gives you satellites that it never saw during training. And so you see in your far right is a satellite which has a bus and 2 extended solar panels. This is a pretty common structure seen amongst many different satellites. And so it does a great job there, as is kind of expected, because that satellite falls within the kind of distribution of data that it had seen during training. Then when we get to satellites that are weirdly shaped, I think this is Herschel, which is mostly a bus, but then this weird antenna going on. It doesn't do so well. And that's because this is something it never sees during training, and so it performs poorly. Similarly for this one here, where this is like a bus with an extended solar panel, but it's kind of at a weird angle. So again, it does a poor job. And so that's kind of where the literature is going in this direction right now, is in doing both shape and pose estimation of unknown targets. And unfortunately, I don't have much more to show because this is where the freshest literature is. I mean, there's some things that are a bit fresher than this, but this is where we're at. So if you want to work on this problem, you can come and join us. So with that being said, I'll show you a quick demonstration using machine learning, because I think we're at 40 minutes, and Yuji would also like to give his presentation. And demonstration is a strong term for what I'll show you, but the hope is that you can use this for your projects. So what is this? Well, so the first network, the second paper that I talked about actually has a MATLAB implementation that you can actually use in your projects because it's open source. It's linked there. You also need the SpeedUE-Cube dataset, which is a dataset of about 30,000 images of a CubeSat. And the really nifty part, and the reason you can use it in your project, is that it also has about 1,200 images from a sequential trajectory. So you can think about using that trajectory as part of your project. I included there for your reference, again, kind of the diagram of the network, but you kind of already know what it looks like. Again, an object detection scheme and then a key point regression.
This is a big bonus.
Sorry?
It's a big bonus.
Big
Bonus.
bonus. Oh, yeah. Yeah. Well, we'll see. So if you were to train the ODN and KRN, big warning that it takes about a day for each one. So I trained them for about a day on each one, and then I released the weights to you guys on Canvas. What I also did is I released, I published only the sequential trajectory portion of SpeedUE-Cube. SpeedUE-Cube is about 40 gigabytes. Also takes a long time to download. I don't know what you guys' download speeds are like, but mine are not great. So I included both of those things. So in theory, if you wanted to use this for your project, you could just download the weights, download the trajectory portion of the data set that I included on Canvas, and then have some fun with it. Great. So here's a quick video of sample results. So you're seeing the images from the trajectory. The bounding box is in red. It's maybe a bit faint. On my laptop, it looks great. And then you see that the key points that are being regressed by the network are being projected onto the image. And you see, again, this network is doing a great job with the Earth in the background. Cool. Okay. So let's conclude here. So, we started with this topic of why do we want to get close? And so for missions that do require this nearness but don't allow for cooperation, we've seen that vision-based methods are kind of a nice strategy with some drawbacks. Classical computer vision techniques allow us for okay pose estimates, but the advent of machine learning has really kind of boosted this topic and has allowed for really precise pose estimates and robust estimates as well. That's not without its own drawbacks, but it seems that data augmentation techniques and the use of kind of space surrogate environments allows us to kind of estimate those drawbacks pretty well. But as I've mentioned tirelessly, there's a lot of work to be done here. Flight testing of kind of known targets using these machine learning methods is still to be done. That would be a really cool thing to do. And then unknown target, refined shape estimates, and pose estimation is what I work on. And so I think it's the coolest thing to do. Finally, I'll end by saying that research in general is a really big team effort, and so it's important to thank always the collaborators. There's more than these. These are the ones that I've met, so those are the ones that I included. But exactly, the alumni I unfortunately have never met, so I included these. Thank you, and if you have any remaining questions, I'll take them now.
For lack of a better term, what's the resolution that the neural net sort of outputs on the satellite shape model? Like, what's the smallest feature you've been able to detect?
I'll let you answer that question, Emily.
We haven't quantified the smallest feature, but
just to give some background, these are like shape primitives that have like a kind of limited number of parameters
representing them, and then you render it with you convert it to like a mesh representation with PyTorch 3D. So I think you're probably ultimately like limited by the density of the like nodes on the mesh. I think there might be a constant number of nodes, so maybe you're not limited by that in particular, but yeah, it's kind of handling it can get tricky when they're small, probably.
But to complement, Emily, your answer, you have to see this network as an initialization. So it provides the superquadrics that describe coarsely the shape from one image. Then you refine it over time, and there are different techniques that we're exploring to do that. One could be, for example, you have Gaussian splatting, 3D Gaussian splats.
I was ready.
and then you get to a very high resolution. You could get to that. But much faster than what you would do without a prior from a neural net.
Yeah.
So, if I understand correctly, like you're estimating pose just directly from a single image, is that correct?
For the one that we're also estimating shape?
Or not the shape one, but for the other,
Yeah.
I think the other two techniques?
Also for on the shape.
Yes. Actually.
Okay, so for
all of them.
All of them.
Yeah.
I recall like seeing a video of like Tango, where like there were like certain like frames where the illumination was really poor, right? And if I had just like seen that image as a human, like there's no way I could estimate the pose. But seeing the video form, like how the shape evolves over time, like I could use that video information to estimate the pose in the situations where the illumination is really bad.
Yeah.
So I guess my question is like, is there any effort to utilize like knowledge from like multiple images over time to improve these pose estimates and shape estimates too?
Yeah, I mean, to some extent, that's what you're doing with temporal filtering, right? So if you like use some sort of EKF, say you get a bad measurement, you can still get a pose estimate because it's part of your EKF time update.
Paul cited a paper where we do that exactly. So the net generates those key points, which are used as measurements by an uncentered Kalman filter. The uncentered Kalman filter refines the pose or determines the pose over time using knowledge of the dynamic, which is equivalent to what you are saying in video. Why do we understand it? Because there is a dynamics evolving. So the Kalman filter injects that knowledge, and then the output of the Kalman filter can be used to retrain online the net, some layers of the net, to make it more robust to those situations. So that's number.
I think this is the UKF one, and then so 9 and 10 is kind of what you want
9
to
and
look
10
for.
of the paper. So where we do that, but certainly there is much more work needed to understand memory loss and the overall applicability of the methodology to render it really operational.
Cool.
And there is the dilemma, because normally when you speak about machine learning and you train a net, you dislike the word overfitting. You don't want to overfit. But when your mission is to navigate with respect to a target, and that's your mission, you want to overfit. So there is it's not detrimental that you are ruining the generality of the net during that mission. But these are all things that obviously needs to be investigated and so forth. Because usually in community wants to keep the generality of the net to be able to be applied to all other scenarios. But that's not necessarily the goal for certain missions.